So in the last class, that is lab third, we have studied how to design a MOSFET using synchronous TCAT tool and how to see the various variations regarding uh, for variations with respect to different voltages and ID/VDS current with respect to VGS. Similarly, ID/VGS variation with respect to VDS. So uh, if you have noticed in the last experiment that for variation, for each and every variation, we have to change the value and again run the simulation. For example, if I want a plot for ID/VGS for let us say VD equals to 0.5. So I have to make VD equals to 0.5 and run the simulation. So I'll get a curve of ID/VGS for a different VD. Similarly, if I want a similar curve for VD equals to 0.7, I have to again manually change that value and run the simulation. So this is tedious job. Every time we need a variation graph, we need to change the value and we have to plot the graph and run the simulation. So this is not practically understandable for the large practical applications. So let us say if we want the ID/VGS relations for 100 values of VDS or 1000 values of VDS. So for that, this simple technique is not feasible. For that, we have to go for the advancement of the tool. So in this lab particularly, we will see how we can parameterize the value. For example, we need the variations for 1000 values. So how we can use that and how to use it in a tool, we'll understand in this class. For that, I'll just share my screen. So I have shared my screen. So what I was telling, I'll just uh, show you. So this is, for example, this is a simple graph of ID VDS variation for P device. Any P device I have constructed and I am showing the ID VDS variation for different values of VGS. So you can see this, there are almost 50 to 60, 70, all more, 100 graphs are there. For each graph is representing different value of gate voltage, that is VGS. So this type of, if I want this type of graph, that means ID VDS relations for 1000 values or 100 values of VGS, that whatever the technique we adopted in the experiment number 3, that is not feasible. We have to go for some other parameterization. So for this type of variations, which is particularly needed for research purpose or any observations, so we have to do the advancement in the tool. So the traditional process what we are following is same. The traditional process what we are following were the same, but the process to use that tradition will change a little bit, So for that, I'll just again, what is our lab 4? So lab session 4 is to design and simulate double gate MOSFET. We'll design a double gate MOSFET in 45 nanometers technology. We'll design a double gate MOSFET in 45 nanometer technology. Plot its ID/VGS and ID/VDS. We'll plot its ID/VGS and ID/VDS and use it to make a circuit. So now what is the use? Why we are doing this ID/VGS and ID/VDS for a MOSFET? We'll see here. So we will use this particular values, whatever the ID/VDS and ID/VGS values we get from the Synopsys TCAT tool, we'll use it to make the tools in the Cadence. You are already using Cadence in a digital VLSI design tool and analog IC designs. So whatever the device you have constructed, for example, if you have constructed a MOSFET or double gate MOSFET, using their characteristics, how you can import that characteristics in a Cadence and how you can plot or make different circuits in the cadence and compare it with the traditional MOSFET. There are already GPTKs available in the cadence, like GPTK 45, GPTK 90, GPTK 180. So you can compare the circuits made up of that traditional GPTK libraries with which you have made with your own device. Whatever the device you have constructed, you can import that device in the cadence. By importing that device in the cadence, you can use them to make circuits. Once you make the circuits, then how you can use that, how you can compare that circuit with the MOSFET based circuits. This is all about session 4. So as I told you, for that I need IDVGS and IDVDS values for thousand variations should be there. So how it can be performed, that we'll see in the two course. So this is lab section 4. So traditional way, as I told you, it will be same. There will be SD in which we'll design our device. Designing device, that means idle will write a script or will construct the device. Then S device will run the simulation. For running the simulation, we will use S device, and then for visualization, as we will use as visual. So what are the changes we have to make, that I'll show you. So this is the changes. Normal SCM file, whatever the normal SCM file we were using, and now we want to use it for parameterization. That tool is synchronous workbench. So in the workbench, we can parameterize the value. For example, instead of giving some fixed value to a particular variable, we can give a parameter. For example, for VD, instead of giving 0.5, we will give a variable VD, and we can assign large number of values to VD. That we will show in the due course of experiment how it can be done. But major thing is that we can give 1,000, 100, how much values we want for VD we can give. So for that, we have to make certain changes in our files. So this is the normal SCM file which we were using for the first 3 experiments. Whatever we are using, this was a normal SCM file. So for the saving structure, what we were giving, the name underscore SD. For saving that structure, what we were giving, whatever the name of your device underscore SD. Here, instead of this, we have to give the command syntax n at the root node at the rate. This is the syntax. Simply, whatever SCM file you are using for normal simulations, the only change is that you have to change it by just dgt underscore sd with this command. Similarly, if you are saving the mesh structure like this, so you have to change the command with this dgt underscore msh. Instead of that, you have to use n at the root node n. Correct. So this is the change which you have to make in the SCM file. Whatever the SCM file you are using, this is a particular change. How you will make change, that I will tell you. But this is a basic process what we have to follow. Similarly, CMD file we were using to run the simulation. So for saving for grade, for plotting the structure, for parameters, for plotting current and output, we were using this syntaxes. So you have to simply change this syntaxes with this syntax if you are using in the workbench tool. You are using the workbench tool instead of normal Synterest TCAD. So whenever you use the CMD file in the synchronous workbench tool, these syntaxes should be replaced by this syntax. You have to just change this syntax with this syntax. This is the second most change which you have to do in your CMD file. Third is this parameter. This I will tell you later. So any doubt in this? So why we are using SWV tool? We are using SWV tool so that we can get the for any relation, IDVGS relation or IDVDS relations for the large number of variations. This, instead of VD, if we want the variation with respect to temperature, for example, all the simulation which we are running are in the standard temperature, that is 273 Kelvin. If we want to see the variation in the current with respect to different temperature values, so what you can do, you can give some variable to the temperature and you can assign the minimum value and maximum value, whatever the minimum value of temperature you want and what is the maximum value of temperature you want. And between that, how many values you want. You can give that and you can run the simulation. You will get the current for different values of temperature. In this way, you can use the tool. Next thing, is how to import it in the cadence that we'll see in the later part of the experiment lab. So any doubt regarding this? So I guess no doubt is there. Shall continue. So now next thing, what I'll tell you how to parameter, how to give a parameter, how to give a particular parameter to a value. For example, if you can see here, I am parameterizing VD. I am not giving a fixed value to VD. I want the VD to vary from 0.0 to 1.0. That is 6 values. For 6 values of VD, I want the IDVGS relation. So instead of giving a VD a fixed value, I have given a value. I have given certain variable that is VD, and this is a syntax. Whenever you are giving a variable, it should be between at the rate. So it is between at the rate. So in this way, you are not giving the value of VD. You are just giving a parameter to VD, and now you can give as much as value for the VD you want. So these are the different graphs for different values of VD. Similarly, if you want to parameterize the doping concentration of certain region. For example, I want to vary the doping concentration of body in a MOSFET. I want to vary the see the variation in the current with respect to doping concentration of the body. So what I did here, instead of giving a value like 518 some value, I give a variable n body NBDY to a body doping, and these are the four values for that body for which I want current. So I just give value 1 is 17, 18, 19, and 20, and I'll get the different graphs with respect to different body doping concentration. So in this way, you can vary the different parameters. Similarly, you can vary the mole fraction, you can vary the temperature, you can vary the VDS voltage, you can vary the channel length, anything you can vary. How to do it, I'll show in the due course of the experiment. Now, in the first class, as I told you, as I told you, that there are two ways to construct a device. Either you write the SCM code, or either you can construct the device, So while constructing the device, what you have to do, that I'll tell you. So while constructing a device, what you do is, these are the steps I have written, that you open the SD window. So while constructing a device, you need to use it. For example, double gate MOSFET you want to use in the SWD. Instead of writing a SCM code for that, you want to construct that DG MOSFET in the SDE GUI mode. So for that, what you need, creating the structure in SDE, simply like whatever you do in the first and experiment, Just open the SD window. So before starting constructing the device, you have to just turn on the general file. There is one option of general file. You just go on that tab and open a general file and save it. Turn on the general file and save it, giving by name. You should can give any name to your general file and save it. And whatever the process you follow for the constructing a device, you make the device, you set contacts, you apply doping, you build mesh, follow all the process similarly what you have done for the last experiments. Just at last, you just turn off the general file. Whatever the general file you have turned on, you have to just turn off the general file and then clean that general file. Once you follow these three steps, that is, in starting you turn on the general, at the end you turn off the general, and after turning off the general, just clean that general file. So once you do that, whatever your working folder will be there. So whatever your working folder will be there a simplified GRL will be generated. There will be one file whose name will be whatever the name you have given to your GR file. For example, you have given the GRL name DG MOSFET. So DG MOSFET simplified GRL file will get generated. So this will automatically get saved in your working folder where you have constructed the device. So now this simplified GRL file you can use it as SCM file. So instead of SCM file, if you want to use a GRL file, that is you have constructed some device and now you want that file to be used in SWB. So you can use simplified GRL file. How to use it? Again, while demonstrating, I will tell you. These are the basic steps. So there are two ways to construct a device. Either write the SCM, that is scheme syntax. For that, what change you need to do, I already told you. You have to just make that changes in your normal SCM file. Similarly, when a simplified GRL file will get generated, it will be like this. At the last, there will be commands like this. I'll show you how it is. So this was the name of GRL file which I generated while constructing a DGMOS. This is the name I gave to my GRL file. So if I want to use it at normal SD, then it is fine. But if we want to use it as in the workbench, so these changes I have to make. Wherever there is DGMOSB, I have to replace with N at the root N. You can see this wherever DGMOS is there, I have just replaced it with N at the rate node at the rate. So you have to just change this in your normal simplified GRL file. How to do it again, I'll tell you in the due course of experiment. So this is the basics how to use the SWB tool. Now I will show you how it is done. Any doubt? What you have to do that I have told you. So there are two ways to construct a device, either write SCM file or make a device. If you make a device, you have to turn on the general. And once you turn on the general and turn off the general file, there will be a simplified GRL file will get generated. In that GRL file, you have to make certain changes with respect to SWB. And if you are writing the SCM file also, in that also you have to make certain changes. So in the SCM file, the changes are very less. Only two changes you have to make. In GRL file, there are 5 to 6 lines which you have to change. In the CMD file, since CMD file is common for both the cases, the changes I have already told. Now I will open the lab. So as I told you, there are two ways. I will demonstrate both the ways how to do it. So first, I will tell you if you have a SCM file with you. If you have a SCM file with you, how to use it for using it in SWB. So first, I'll just create a new folder, TEMSWB. So first, I'll need this setup file. I'll just copy this setup file, copy. Yeah. So this is, as you know, this is used to run the tool. So what I have to do, I have to just make a SWB workbench. So what I'll do, right click, open in terminal. I'll open the SWB tool now. TCSH. So just press. Now this is your SWB workbench. This is your SWB workbench. Now you can see this. It whenever you open the SWB, it will look like this. This is the interface and GUI mode of SWB. Now I have to make a DigiMOS or MOSFET. Anything I can demonstrate. So what I have to do, I have to go to project, new, traditional project. I have to just go tool, new, and traditional project. Now I need to save that project. I need to save that project. So just click here, save current project is there. Just click here, and there will be TMP. Just after TMP, give a backslash, and whatever name you want to give, you can give. I'll just give a name DGM. I'll just give a name DGM, and I press OK. So you can see this here. There was a temp folder. I just generated one project which is name is DGM. You can see I can generate any number of project in this temp folder. So I have generated one my project that is DGM. Now I need what I need. I need tools to run the simulation. I need tools to run the simulation. So you can see this. There is no tools. There is written no tools. So I have to add the tools. I have to add the tools. So for making the device, we need SD. We all know for making the device, we need SD. And for running the simulation, we need S device. For running the simulation, we need S device. So first tool I will add that is SD. So I'll just right click here. There is option of add. I'll just click add. There is option of tools. I'll click tools. There is option of SD. I'll just click SD. Okay. So you can see this SD tool has been added. Their SD tool has been added. Now second tool I need is S device. So what I'll do, I'll just again right click here, add. Now I want S device. So again, I'll go to tools. From here, I'll select S device. Okay. Now there is two options after selected tool or before selected tool where you want to add the S device. So we want all S device always after our SD. First we will construct the device, then we will run the simulation. So it will be after selected tool. By default, after selected tool is added, so you don't need to do anything. Just press OK. So once you press OK, S device is already also added. So this is the way to add the tool. This is how you can add the tool. First, how to make a project that I told you. Don't forget to save that project. Once you save that project by giving any name, it will be shown there. It will be shown in the right side. So whatever the process you will do, that will do inside that project. Now this SDE and S device has been added. This SDE and S device has been added. So now what next we'll do? We want to add the SCM file. We want to add the SCM file. Either we can SCM file or we will add GRL file in the SD. We want the input to SDE will be either SCM file or GRL file. So in the first part, I'll show you how to use SCM file. So what I'll do, I have SCM file with me. I'll copy that. Take it. Let us say I'll copy this SCM file dgt_t.scm. Just open this. This is a normal MOSFET SCM file. So what I'll do, I'll just open this SCM file. Control A for select all, for selecting all. Control C to copy. Control A for selecting and Control A for selecting all, and Control C to copy. Once I'll copy, I'll just close it. Close this. This to be added to SD. This SCM file is to be added to SD. So what I'll do, right click on SD. There is one option of edit input. There is one option of edit input. I'll just go there and select commands. I'll just go there and select commands. You can see that there will be an empty screen will open. So what you do, you have to just paste it. You have to paste the, so Control V. So all your SCM file, whatever the SCM file you have copied, it will get placed here. It will get placed here. So in the starting, I told you, you have to make changes. This SCM file will not work in your SWB. You have to make changes. So what changes you will make? So instead of DGT_SD, you have to give it N shift @ NODE @. Similarly here also N shift @ NODE @. Only these two changes you have to make for in the SCM file. Only these two changes you have to make in the SCM file. Rest of the SCM file will be same. Nothing you have to make, nothing change you have to do. You just save it. You just save it. And close it. Now you have added the SCM file in the SD. You have added the STM file in the SD. Now you want the CMD file. Now what you want? You want the CMD file. So for that, again, I'll copy the CMD file. Get. From anywhere I can copy the CMD file. So this is the CMD file. This is the CMD file. Again, I want to copy this CMD file. What I will do? Control A to select all. Control C. Just close it. Again, right click, edit input. This I am adding in S device commands. Control V. Now I have added the CMD file. Now again there is need to change in the CMD file. That I have already told you, but again I'll tell you. So these are the changes which you have to do in the CMD file. Normally CMD file in syntax are like this. You have to make it like this. This syntax you have to change. So I'll make the necessary changes in the CMD file. This will be, grid will be @ TDR @. Similarly, plot will be @TDR DAT TDR DAT . For this case, for the normal MOSFET, I am not using any parameter files. So I'll just delete this line for this demonstration. I'll just delete this line. Current will be @ PLOT 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 and output will be @log . So these are the changes which we have to make in the CMD file. Also, now we want the variations for VDC for different values of VD. So here, instead of giving, you can see this here, drain voltage is 1 volt. Drain voltage is 1 volt. So we don't want it for 1 volt. We want it for different values of VD. So instead of giving it a fixed value, what I'll do, I'll make the change here. I'll give some variable. So syntax is we have to give the variable inside @. For example, I'll just give the VD shift @. So my variable is instead of giving VD, I'll just fixed value to VD. I'll just give a variable @VD . Now I'll save it and close it. Now I have added both S device, CMD file to S device and SCM file to SD, and all the necessary changes also I have made. Whatever the necessary changes required, that I have already made. Now I want to give the values to variable. So again here, right click, add parameter values. Just click on add parameter values. So what was our variable? That was VD. So now please note that temperature, VD, these length, these varies in linear scale. These varies in the linear scale. But the doping concentration, whatever the doping concentration will be give, that varies in the powers of 10. That is in the log scale. So please specify the scale also. If you are varying the doping concentration, then the scale will be log. If you are varying the normal linear scale values, then it will be linear. So I am varying the VD, which will be linear. So I'll just select linear. So minimum value, whatever the minimum value I want. Let us say I want 0.0. I'll start from 0.0. And maximum value I want 1.0. So how many values we want? That is you want 10 values, 20 values, 15 values, 5 values. That number of values you can specify here. So for just demonstration, I'll just give the value 6. I want 6 values. Once I press OK, you can see this, all the 6 values appears here. Apply and press OK. So you can see this. Now there are 6 values of VD. There are 6 values of VD. So now you have to just run the simulation. You have to just run.
How these values are added, voltage.
I'll just again tell you. You just click here. Here is the option of add parameters / values. You just click here.
So that VD will come automatically when we
no, you have to
add
give.
it
You
into
have
the
to give
CMD, right?
parameter. Whatever the variable name you have to give in the CMD file, that you have to mention. Please make sure that the name should not change. With the capital small also. That is case sensitive. If you give there VD capital V and small d, and here if you give small v and small d, it will not take. The variable, whatever the value you have given.
We need to click on the first column, right click, and then add new parameter.
No, there For example, if you have changed there are some values which you can change in SDE file, and there are some values which you can change in the CM. For example, doping concentration are there in the SCM file. So that you have to change in the SCM file. But the voltage, temperature, this is in the CMD file. For that you have to, so you have to, if for example, I'll just close this. For example, if you want to make change in the doping, so instead of clicking SD, you have to click here. Same, add parameters. I'll show you that also.
Got it.
I'll show you that also. So now simply you have to run the simulation. So there is one option of run. Oh, first I have to select what I have to run. So I have to run all the nodes. I'll select all the nodes. And just press run. Yes. So one thing, whenever you run the simulation, if it is running, there are some options. If it is in the queue, will be light green. If it is running, it will be light sky blue. If it has run, it will become yellow. And if it fails, in some cases, if something is not matching, some values you have given is not matching, it will fail also. In the case of fail, it will be red. I'll show you that also when it will fail and how to rectify that. So right now, it is running. It takes some time. Depending upon the speed, it takes some time to run the simulation. So normally, if you run 100 cross 100 values, so you have to just run it in the for run it, and just after 3 to 4 hours, you'll get the values. Sometimes it take days. If the number of values are more, then it take days to run to simulate. Now you can see this, all the values, all the simulation has been done. Now I want to visualize the result. What I'll do, I'll select it. And there is one option here for visualization, that is as usual, click here. First option, select it. So here you have to search for design.plt file. It will be in the form of nodes. So for example, one is n2 design.plt, then n4. You have to just select design.plt file, n5, n6, n7, and n8, and just press OK. So you can see this, all the files have opened. So I'll just 1, 2, 3, 4. Press Control and select. Now this gate voltage we are giving VG is the outer voltage, will plot in x-axis, and current will measure from drain. So drain, total current, right y-axis. So you can see this. There are N4, N2, N5, N6. There are different graphs with respect to different values of Vg or Vd. This is Vd equals to 0. This is Vd equals to 2. This is Vd equals to 4, 4, 0.4, 0.2, 0.6, 0.8, and 1. We have given the 6 value. And if you can see this, as Vd is increasing, the current is also increasing. That is absolutely fine with the MOSFET. For increasing the Vd, if the Vd drain voltages increases, the current increases. So in this way, this is I demonstrated with using MOSFET. You have to just use it to demonstrate the double gate MOSFET. You have to just construct a double gate MOSFET and you can use it to demonstrate for the double gate MOSFET. So this was the one way. This is the one way, that is if you have SCM file with you. If you have SCM file with you. Now, if you want to construct the device by yourself, so for that, again, I'll tell you, I'll create a new folder, BE MOS demo SW. Wait. So first, what I need to construct the device. First, I need to construct the device. So first, copy this. Paste. So for constructing the device, I have to open SD. For constructing the device, I need to open the SD. So CCSH. Enter. SDE. So as I told you, before starting construction, you have to turn on the GRL file. If you don't turn on the GRL file, and nothing will be recorded. So before starting constructing itself, you have to turn on the general file. So that I'll do. File. There is one option of journal. If you can see, there is one option of journal. I'll just turn on it. Turn on the now. You have to give any name to general file. Whatever name you want to give, you can give. Let's it to be M3D. Whatever name you want to give, you can give, and just open it. Now GRL file is open. Now whatever the process you use to construct, you can use. So what we'll do, view GUI mode to be 2D, draw, auto region naming of, draw, exact coordinates. So I'll construct a double gate MOSFET only. I'll just construct a double gate MOSFET only. So first I'll construct the source region. All the source, drain, and gate will be of silicon. So what I'll do, I'll select rectangle from here. I'll just construct a rectangle. So the length of my source region, it is 30 nanometers. So it will start from 0.0 and it will goes to 0.030. 0.0 to 0.030. The height of my total device, is let's say 20 nanometers. So it will start from 0.0, 0.02, 0.0, 0.020. So this is my source. This is my source. SOUR source. I'll give it as. I'll just press OK. Now I'll just select XY coordinate. I'll just select the XY coordinate from here. So this is my source region. This is my source region. Now second will be my channel. My second will be my channel. So channel, let's say it's 45 nanometers. It is 45 nanometers. Again, I'll create the rectangle. So my source is starting at 0.030 and my channel is 45 nanometers. So 30 plus 45, that is 75. So my channel will start end at 0.075. 0.075. This is fixed all across my device, that is 20 nanometers. So I'll not change it. 0.020. Okay. I'll give the name channel. See. Okay. So this is my channel. Now I want drain region. Similarly, so my channel is ending at 0.075 and it is 30 nanometers. So it will go to 105. 105. This will be same 0, 20. Okay. So all my source, channel, and drain is defined. Now I want to define two gates. Two gates I want to define. So now the gates, before gate, there will be oxide layer. There will be on oxide layer. So I have to just select the oxide from here. I have to change the material. Don't forget to change the material. So I'll just change oxide. So oxide will be only where my gate is there. So gate is from 30 to 75. 30 to 75. And there are it will be on the top of my device and at the bottom of my device. So this is 20 nanometers. This is 20 nanometers. So let us say 2 nanometers thickness oxide I am placing. So it will go from 20 to 22. Above in Y direction, it will go from 20 to 22. And in X direction, it is from 30 to 75. So I'll just make a rectangle. So in the X direction, it will go from 30 to 75. In the Y direction, it will be from 20 to 22. Okay. I'll just give name O1, oxide 1. So this is my oxide 1. Similarly, oxide 2 will be on the downside. It will be on the downsides. So this point is 0 with respect to Y. This point is 0. So it will from -2. It will start from -2. So I'll just make a rectangle. In the X direction, it will be from 0.030 to 0.075. In the Y direction, it will be from 0.002, that to minus 0.002 to 0.00. 0.00, since it is downside of the wire. Okay. I'll give it the name O2, oxygen. Oh, okay. So this is oxide layer. Now I want to place the metal. Either you can place polysilicon or you can place metal. Whatever you want, you can place. So I'll just place metal, aluminum here. You can see this, there is polysilicon also. You can use polysilicon also to construct the metal gate. This is aluminum. So again, the aluminum metal will be on the top of my oxide. Let us say 5 nanometers of aluminum I am using gate metal. So I'll just draw a rectangle. So it will be from 0.0 to 0 to 0.075, and it is just above the oxide. So in the top, oxide is from 0.022. It is 5 nanometer to 27, 0.027, 0.02 to 0.027. Okay, I'll just give the name G1. Yeah, front gate FG. Okay. Similarly, back gate, it will be same 0.030 to 0.075, and it will start from 7 nanometers. That means 7, that is minus 2, minus is right, 0.002, from -7 to -2. Okay, let us give the name backgate B. Okay, so now I have constructed my device. My device has been constructed. Now I want to give the context. There is source, drain, front gate, and back gate. So again, go to context set. So first contact will be front front underscore gate, GATE gate set. Then back gate, BACK back shift underscore gate, GATE gate. I'll change the color 110 set. Similarly, source, SOURCE source. I'll change the color set. Now drain, DRAIN drain. Set. Now 4 contacts have been set. Now I have to apply it. Here I have to select the pointer. Here I have to select the edge. So first contact is front gate. I'll just select this, activate it, place it here, contact, set contact. Next is back gate, activate it, place it, contact, set contact. Now third is source. I'll first place drain, activate, place, contact, set contact. Now last is source, activate, contact, set contact. Now all the 4 contacts are set. Now I want to dope. Now doping, if it is an NPN transistor and MOSFET, then and double gate, then this to be doped with phosphorus and body will be doped with the boron. So device, constant profile placement. I will select region. So first is source region. I'll just give it name S. Here also S. I'll dope it with phosphorus 1E90. 1E90 at placement. Now second is drain. I'll make it D. This is the same concentration, same material, add placement. Now third is body, that is channel. I need to dope it with, I'll just make C. See, I have to dope it boron, and that too lightly doped. I'll make it 16. Add placement. Now all the placements are add. You can see also source, drain, channel. Now you can close it. Now doping is done. Now last is mesh. So what you will do? Go to mesh, define referral window, that is rectangular. Okay. Go to mesh, refinement placement. Minimum size I'll give 0.01. Maximum size 0.01. Minimum size I'll give 0.005. 0.005. Create refinement. Close it. Now mesh, build mesh, build mesh. Just close it. Fine. First I'll save the model. Save model. SDE MODEL. Any name you can give. I'll just give a. Then file. I have to, whatever general I have turned on, I have to turn off that general. Turn off. Again, file, general. I have to clean it. Again, it will ask, don't change the name here. Whatever the name you have given to GRL file, same name you have to give it, and just open it. Now you can close the structure. So you can see here, a simplified GRL file has been generated. A simplified GRL file has been generated. Normal GRL file is also generated and simplified. You need this simplified GRL file. I'll just open this. So this is a simplified GRL file. Now here, I want to use this for S device. I want to use this for S device. So what I'll do? Open in terminal. Enter. Setup. SWB. I'll just open SWB. Okay. Again, project. New. Traditional project. Save the project. I'll just give name /t GM DGM12. Okay. So this is, again I'll add the tools. Add SD. Okay. Okay. Similarly, X tool, add tools. No, no, as device. I need to add as device. Okay. After the selected tool. Okay. Now, instead of copying the SCM file, I have to copy the simplified GRL file. So I'll just copy the simplified GRL file. Control A, Control C, close it, close it. SD, added input, commands, Control V. Now, as I told you, you have to make the changes here. Whatever the change, what changes I told you, wherever SD model is there, you have to just make it n at the rate node n at the. I'll just show you also. This is the change you have to make in the GRL file. This changes you have to make in the GRL file. So I'll just make these changes in the GRL file. Up to here it is same. Project name, save model. Project name will be and shift at the rate NODE shift at the rate. Now set IO controls output file instead of SN mesh SD model. You have to give SD shift underscore DVS. Now for meshing command SN mesh, it is just like that. Project name at the rate node at the rate. And shift at the rate NODE node at the rate. Again SD model. It will be and shift at the rate NODE shift at the rate. Build mesh and shift at the rate NODE node shift at the rate. System command. Fill out this. And shift at the rate NODE at the rate. Save model and shift at the rate and save it. Save it. Now as device, so I have already modified the If you can see this, I have already modified the code for this. If you can see, I have given the front gate and back gate. There are two gates. Since there are two gates, I have given the two gates, and rest of the things will be same. Rest of the things will be same. Instead of one gate, there will be two gate, front gate and back gate. Here it is VD sweep. I am plotting the VD sweep. So VD is changing from 0 to 1 with the gate voltage 0.50, 0.50. Here I'll show you how to vary the temperature. I'll show you how to vary the temperature. I'll just copy this code. This change you can make. This was a normal CMD file for MOSFET. There was only one gate. I just do it. Whatever the gate was there, I copied it twice. So it will be front gate and back gate. So I'll just copy this code, Control A, Control C, close it, close it, S device, edit input, commands, Control V. So all I have placed here. Again, I have to make these changes. Grid will be at the rate TDR shift at the rate plot will be at the rate TDRB80 shift at the rate parameter I am deleting. I'll just show you in the last how to use this parameter file. Delete. Current will be at the rate PLOT plot at the rate, and output will be at the rate log at the rate. Now save it. Again, I want to vary the temperature. If you can see, this temperature is fixed to 300. Temperature is fixed to 300. What I'll do, I'll make it a variable. Shift at the rate, let us say capital T, shift at the, save it, close it. Let's see it works or not. So again, I have added SD, I have added S device. Now I have to add the parameter. What I'll do, add parameter. Now my parameter is T, list of values linear. I can give the list of values also. Whatever values I want, if manually I can enter also, but I want linear. Minimum value will be 250, 250, 300, 350. I'll give it maximum value 350. Total number values 3. Okay. You can see this, the 3 values of temperature has been allotted. Now it should run. If I have not done some mistake. That means device is right. There is some mistake with the temperature. I have to see what the mistake I have done. clean up node. So that means in the SD there is no problem. Something wrong with the S device. I have to see. Edit into commands. Just control A, delete. Activities. Tcad. So you are save it. Control A, Control C, close it. Add, edit input commands. Control V. Delete. Shift at the rate TDR. Shift at the rate plot. Shift at the rate TDR DAP. Shift at the rate plot current. At the rate CLO. At the rate log. At the rate LOG. At the rate save. Front get back at source. Everything is same. Save. Close. Now I'll just clean up this node also. Now I'll just change the doping concentrator. See whether this was, instead of giving a 6 at the rate TBY shift at the rate save close add parameter T body. Now I told you the variation in the doping concentration is with in the log scale. So what I'll give, I'll choose the log scale. Minimum value I'll give 1E15 and maximum value I'll give 1E17. 1E15 is the minimum value and maximum value is 1E17. Number of values I'll want 3. I'll want 3 values. The scale is log. Okay. Now run the simulation. Now it is running. That means close it. Now I'll show the result. N10 design.plt, N3 design.plt, and design.plt. Okay. X-axis. Drain. Total current. Right. So in this way, there is some, I have not given the values, maybe right. That is, it is showing like this. But in this way, you can get the graphs for different variations. Editing commands. Okay, I'm giving the gate. I am varying the drain voltage. I'm plotting the gate voltage. That is why it is showing like this as visual. N10 design.plt, N3 design.plt, and N8 design.plt. Okay. The voltage which I'm changing is drain voltage VD. Drain outer voltage. X-axis total current. Right. So you can see this. These are the different graphs. These two graphs are overlapping. That's why it is not showing. That is a variation. If you increase the doping, that 1E15, that is for 1E15 the current is less, but for NE16 and NE17 the current is almost same. That means after, if you increase the doping after certain level, that is NE16, if you increase the doping after that, it will hardly have any effect on the current. So these types of results you have to write. So this is the variation you can show with the help of doping concentration. Now, two most important things which I have not mentioned here. First thing is, if you want to vary the channel, these are independent variables. These are independent variables. If you can notice, these variables are independent. That means if you vary the body doping concentration, it is an independent variable. It does not have any, if you vary, it will not change anything else. But similarly with the VDS, if you are changing the VDS, it does not have any effect on any other parameter. It does not have any effect on any other parameter. But in case if you change the channel length, for example, I'll show you. For this, I'll just close this. So this example I have made for you to show the variations. So for example, if here, let us say whatever the MOSFET we have seen, same MOSFET, initially what we have designed, the source is 100, drain is 100, and channel is 100. Channel is 100. So if we want to reduce the channel, for example, if you want to make the channel from 100 to 90, if you want to make the channel from 100 to 90, then if you change the channel, the source and drain will also change. The source and drain will also change. That is dependent. That means source and drain, if you change the channel, source and drain will also change. So if, for example, if you can see case one is when you are changing, you are making it change by no change. There is no change. That means t value is 0. If you, why I have taken t by 2? If you can see this, why I have taken t by 2? Because the change will be on the both the sides. So it will be whatever the t change is there, that will be divided half on both the sides. That is in the source and in as well as in the drain. How it will affect, I'll show you. So if let us say t is 0, so it will not change. That means it will be 100, it will be 200. If you subtract it from 0.200, if you subtract 0.100, it will be 100. 0.100, that is 100 nanometers. That means the channel length is 100 nanometers only. Let us say you want it to be changed by 10. Total change, that means instead of 100 you want it to be 90. 100, it's instead of 100 you want it to be 90. So then t will be 10, because you are reducing your channel length by 10. So it will reduce by both side by 5 nanometers. So I have used the formula t by 2. So t is 10 nanometers, that is 0.010 by 2 plus 0.100. Similarly, here it will, if you can see this, here the coordinates will increase. It will go from 0 to 100 and it will go this side. Here, because the channel was from 100 to 200. The channel was from 100 to 200. The last point of channel was 200. Now it will shift towards more this side. It will shift this side. That means you have to subtract it from 200. That's why here I have subtracted, here I have added. This t by 2 here added because it will shift this side. I have subtracted because it will shift this side. So once you will add, now your new point for source ending will be 105. Now your source will start from 0 and it will add to 105. That means source length will become, instead of 100, source length will become 105. Similarly, now instead of your drain starting from 0.200, it will start from 195. So from 195 it will go to 300. That means again 105. So total 300. Now 105 is source, 105 is drain. So remaining, if you subtract from 300, that is 90 nanometers. So your channel will become 90 nanometer. Similarly, if you want it to reduce by 20, same formula. Instead of 105, it will shift to 110. And instead of 195, it will shift to 190. That means if you are changing the channel length, if you are changing the channel length, it is affecting your source length as well as the drain length. So the syntax for this will change. The syntax for this will change because here it is not only changing the channel length. It is not affecting only the channel length. It is affecting both source length as well as drain length. I have depicted here in the figure also when the source channel is 100, clearly it will start from 100 and it will here also 100. If channel length is 90, it will start from 105. Here it will start from 190. If so, how to encode it? How to encode it? That I will show you. Similarly, this is the oxide. This is the oxide thickness. If oxide is 2 nanometers, then your gate will, let us say this point is 200. This point is 200. And if your oxide is 2 nanometers, then your gate will start after 202 because 200, 2 nanometers of oxide, 200, then your gate. For example, if your oxide is 4 nanometer, if your oxide is 4 nanometers, then your gate will start after 4 nanometers. That means if you are changing the oxide, if you are changing the oxide, it is changing your gate also. That is dependent. Gate terminal is dependent on the oxide terminal. Similarly, I have depicted oxide thickness plus 200. If oxide is 2 nanometers, then your oxide will end at 202. Then gate will end oxide thickness plus 0.210. It will end at 0.212. Let us suppose your oxide is 4 nanometers. Then the coordinates will changes. Oxide thickness 4 nanometers. Then it will end at 2.204. If you put 4 nanometer here, 4 plus 210, that is 214. So dependent. That means your gate terminal is dependent upon the oxide thickness. If you are changing the oxide thickness, your gate is changing. So I'll just show you this. One intermittent SW. Okay. I want to show you this how the commands is here. So as I told you, so if you change the channel, then your source will also change. This is complete body. This is our complete body. So it will not change. But if you change, this is source, this is drain, this is, if you are changing the channel, your source and drain will change. So instead of giving a fixed value to source and drain, I have whatever I have demonstrated you there, I have written here in the form of syntax. T plus 2 plus 0.100. What will be the value of T? That will be divided by 2. That will be plus 2.110. Let us say T is 10. Then 10 divided by 2, that is 0.5. It will be added 0.005. It will be added to 0.100. Then the source will start from that point. That is 105. Let us say T is 20. Let us say T is 20. So 20 divided by 2, that is 10. So 10 will be added to 100. So your source will start from 0 and add to 110. That means the more you decrease the channel length, the more your source will increase. Similarly, if you can see the drain, it is 200 minus that point. So if it, let us say T is 20, so 20 divided by 2 is 10. So 0.200 minus 0.10, 0.10, it will become 190. So instead of your drain starting from 200, it will start from 190. So and end to 300. If it start from 190 and end to 300, that means the overall length of drain has increased by 10. That is 110. So you have to change the complete command here. You have to change the complete syntax here. Same with the oxide thickness. You can see the oxide thickness. Oxide thickness, if you change the oxide thickness, then your gate will also change. Here you can see this oxide thickness you have used two times, where one with the oxide and second with the oxide. So whatever the oxide thickness you give, for example, 2 nanometers, for example, 2 nanometers, then your oxide will be starting from 200 and it will be 200 plus 2, that is from 200 to 202. And your gate will be gate oxide plus 210, gate oxide plus 210. So if your gate oxide thickness is 2 nanometers, then your gate will be 2 plus 210, that is 212. Let us suppose your oxide is 4 nanometers. Oxide is 4 nanometers. Then this will start from 200 and it will end to 204. This 4 plus 200, 204. Similarly, gate will also change. If your oxide is 4, then 4 plus to this 210, this will become 214. That I have demonstrated here, 214. Similarly, that means if the 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 parameter is dependent, then you have to make the changes like that. So this is, I'll not give you the assignment on this, but for if you are using it in the future, if you are doing some calculations and if you want to use it in the future, I'll provide you all the syntax. Technically, I have told you how to do it. Again, I'll tell you here. This oxide thickness will define the where your gate and oxide will be. If your oxide thickness is 2, so 2 plus, because it is just upon the top. So this is 200 nanometers. We know the length of the total length of our device is 200 nanometers. So whatever the thickness of oxide plus starting point, that is 202, will be the oxide, and whatever the starting point plus oxide thickness plus 210, this will give you the gate. Let us say this is 4. Let us say this is 4. Then this will change to 0.204 and gate will change to 2.14. So whatever this, if you want to change it 5 times from 1, 2, 3, 4, 5, every time you change the oxide thickness, gate will also change. If it is 1, 201, 211. If it is 2, 202, 212. If it is 3, 203, 213. If it is 4, 214, 204, 214. So this, in this way, it will vary. Similarly with the channel, if you are varying the channel, it will vary the source. If you increase the channel, source and drain will reduce. If you decrease the channel, source and drain will increase. And why it is T by 2? Again, I told you कि whatever the change in the channel, that will be divided half on the both the sides. If you reduce the channel by 10 nanometers, let us say you are making it from 100 to 90, then your source and drain will reduce by 5, will increase by 5. That is, it will become 105, it will also become 105. That means it will start from 0 and go to 105. It will start, instead of 200, it will start from 195 and go to 300. And last, what I want to tell you, I'll just close this. So this is the same double gate MOSFET. Say this is the same double gate MOSFET whatever I have constructed. So if you can see this, I'll just open the SD window. I have constructed this edit input commands. So here you can see this. I have used HFO2. Here I have used HFO2. Instead of SiO2, I have used HFO2 as an parameter. I have used, instead of SiO2 normal oxide, I have used HFO2. So if you use some other materials instead of normal oxide, if you use some other materials, so what changes you have to do? Just that I am telling you. So all the things will be same copy of this is GRL file I have copied. So the change is like this. I'll just close this. In the S device, in edit input commands, there is one option of parameter file. There is one option of parameter file. So you just click here and you have to just, this parameter file I'll provide you. This parameter file I'll provide you. You have to just paste this parameter file here. You have to just place this parameter file here. Whatever the parameter file is there, you have to just paste it here. You have to paste it here. What you have to do in the SD, simply edit input commands, just like you paste commands, below that there is a parameter. There is one parameter option. Simply paste, simply paste the parameter file here. And whatever the materials you are using, whatever the extra material you are using, as you do in the normal SD also, whatever the extra material you are using, I'll just close it. So this is, so this is my whatever the device I have constructed, it will be when I open it, when I'll open it, it will be shown like this folder only. It will get converted into a folder only. So it will be inside the temp folder, demo 6 inside demo 6. By default, temp folder will create for every device. This temp folder will create. So whatever the project or SWV file you make, it will be inside that temp folder. So once you open this temp folder, so this is your project. Whatever project you make, it will be inside this temp folder. So what you have to do, what I am telling you, you have to just open this. So whatever the fancy material you are using, you have to just place it here. You have to just place it here. So for example, HFO2. So you can see this HFO2 parameter file is here. I have pasted it here. I have pasted it here because I am using it in my device. So whenever I am using any fancy material in my device, which is not there in the list, so I have to copy the parameter file in the parameter section and I have to paste it in the working folder. I have to paste it in the working folder. Similarly, for I have copied many different parameter files. So since I'm not using silver here, you can see this silicon germanium, Si germanium. Sometimes instead of silicon, we use this fancy material, silicon germanium. So I have just pasted this parameter file, silicon germanium parameter file in my working folder. So whenever I use some fancy material, which is not in the drop down list, what I have to do, I have to just paste it in the working folder. Again, I'll tell you. So from the starting, I'll tell you. So this is my temp folder will already automatically generated. So whenever I open the SWV, okay. So this temp folder, whatever file I will make, this will be inside this temp folder. So if I'll click here, whatever the project I have made, this is inside my temp folder, DGA, DG22. Suppose I want to make some new project. So what I'll do, project, new, traditional project. Now once I'll save it, save. Give it any name. Temp folder is there, just make a backslash, give it any name. DGGGG. Okay. So now this DGGGG is also there. This DGGGG is also there. So what I told you, if you are using any fancy material, what you have to do, edit input, commands. Below the command there is parameter. You have to just paste that parameter file here like this. It will be empty. There will be nothing. You have to just paste, copy. I'll provide you that parameter file. You have to just copy that parameter file and just paste it here. Second thing, what you have to do, since this DGG I have created, you can see this DGG project I have newly created. So its folder will be created in my temp folder. So once I'll close it. If I'll open the temp folder, you can see this DGGG folder is created. It right now it is empty because I have not done anything. So what you have to do, you have to paste that parameter file, whatever the extra parameter file you are using, that you have to paste it here with the models file, with the models file. So this is HFO2, whatever the extra material file you are using, you have to paste it here. So at the last, what is the use of this? What is the use of this? I just want to tell you this. What is the use of this? So I'll open the presentation. One thing I have not told you, I'll just tell you. So once you get the data, what is the use of data? So once you get the parametric variation generated, you can import the TCAD device. Whatever the TCAD device you have constructed, you can import it into Cadence using Verilog A code. With the Verilog A code, you can use it to import it into the Cadence. How you can do it? Simply you have to write the Verilog code. First, what you have to do, this is your Cadence window. This is your Cadence window. You all know how to use Cadence. You all know how to use Cadence. So you create one library. Every time you create one library, inside that library, you create the cell. You create the cell. So all the cells you create is in the form of schematic. All the cells you have created, it will be in the form of schematic. So if you want to import, the your device inside the Cadence, so what you have to do, this library, whatever the cell, for example, you have created a MOSFET, N MOSFET. So just give the name N MOSFET. Instead of selecting schematic, you have to select Verilog. Just drop down, you have to select a Verilog. Instead of selecting the schematic, you have to select the Verilog. From here, you select Verilog. Once you select a Verilog, this window will pop up, and you have to, this code will be there. I'll provide in the future if you want to do the research. This code, Verilog A code is there. You have to just paste this code. So what this code does, it will read the LUTs. It will read the LUTs. Whatever the LUTs you provide, it will read that LUTs. So you have to just copy this Verilog code. So this is the simple Verilog code. So this is what you will get once you simulate that SWV. So as you've seen, I gave the value of VDS 0, 0.2, 0.4. Similarly, here I varied it for 100 times. VDS 0 with respect to VDS 0, this is the current. Then VDS 0.05 with respect to VDS, this is the current. Then VDS 0.10 with respect to that, there will be some current. So I can download this CSV file. This is Excel file I can download. I'll show you how to download it. I can download it. Once I have that CSV file. So as I told you, this Verilog code will read the LUT. This is just LUTs, tables. Whatever the tables LUTs are there, it will read that table. So once you have that CSV file with you, you can convert it into a form of LUT. So this is an LUT. So what an LUT do? For example, if the starting, it will vary the drain voltage. It will keep the drain voltage as 0 and vary the gate voltage. Then it will change the gate drain voltage some, then again vary the SG voltage. And in this form, you will get the current. So it will generate a 1000x1000 long LUT, sample LUT, to be generated using CSV file. Whatever the CSV file is with you, you can generate the LUT. For this, you have to use the Python code. For this, you have to use the Python code. You can use the Python code to generate the LUT. And once you generate the LUT and put it into here, you can create the symbol for your device. And you can create the symbol for your device. So this is the symbol of my device. I have generated one device, that is PGOT, that is I have generated, and I have constructed a simple inverter using that device. Instead of using normal PMOS and NMOS, I have used the device PGOT, which I made using Sinterus TCAD, and I imported it in the cadence. I imported it into the cadence, and I have used it to construct the inverter. And this is the characteristics of that inverter, whatever the inverter I have created. So again, I'll repeat what you have to do. This was the data. This was the data. ID VDS. This I shown you. So this is, once you vary the VD, you can export this CSV. You can export this CSV file. You can export this CSV file. I'll tell you how to export this CSV file. Once you have this CSV file, this Verilog code is there. Go to Cadence. Instead of schematic, select a Verilog code. Instead of select from here Verilog. Once you select a Verilog A code, this type of window will pop up. So just paste this code there. Just paste this code there. So what this code do? It will read IDS, CGD, CGS, whatever the LUT you will provide it. If you don't have CGD, CGS, you can provide the IDS, that is current related LUT to it. So it will read this LUT. What LUT contains? LUT, what is there inside the LUT? VDS value, VGS value, and current value. It will have VDS, VGS, and current value. So using the Python code, you can convert this CSV file into a LUT. This is a LUT. You can simply use a Python code for converting this CSV file into a LUT. Once you have LUT, you can create the symbol. Symbol creation that will be taught you in the Cadence lab, how to create a symbol. So you just paste this code and save it. It will take you to the symbol. You can directly make a box like symbol also. This is the artery work, art like work I have created it. Instead of it, it can be a box also. Whatever you create a symbol, you know how to create a symbol in the VLSI design lab. Now once you create the symbol, you can use that symbol to make the device. So I have to tell you how you can export that CSV file. Activities. You can open in terminal. TCSH. So this I already ran. I'll just plot it to show you how to export the CSV file.
Where can we see the Verilog code?
Verilog code is you can download it. I will provide you, but it is there. You can that you can write also, but you can in this, if you search in the net, you can get from there also. So for your sake, if you want to do something like this research, I'll provide you that code, but you can search it in the net also. You will get in the net also.
For MOS devices, right?
No, this code is for any device, whatever the device you construct, for any device, there will be gate voltage, drain voltage, and current. All three things.
Verilog code is for simulation that you are.
You whatever the LUT you have made, whatever the LUT will be based on whatever the VD, VGS, and ID is for your device, whatever the device you have constructed. I'll show you. I'll show you once. So with respect to your device, the value of current will change. For example, MOSFET have some current, and your device have some more current than MOSFET. If your device, so it will perform better. It will perform better with respect to MOSFET. So you can import your device and you can compare with the GPD case. 4510 nanometer GPD case there in the cadence. You can compare your device, whatever the device, double gate MOSFET or any device you have constructed. You can import it in the cadence using Verilog code, and you can just make an inverter with your device and make an inverter with the normal MOSFET, and you can compare the performance. Yes. Now this graph, if I want to export, what I have to do? Data, export XY. So how many curves I want to export? I have to select all the curves. Export. It will be saved in the form of CSV, whatever name I want to give. DG, MOS, CSV. Save. Once I'll save it, so it will be there. I'll just close it. So this CSV file I have created, it is saved here in my DGM. Whatever my project was there, it will get saved inside this. You can see this. This is the CSV format. If you open, this is opened in the terminal. If you open it in the normal Windows, you will see this is a CSV file. So this is first value is voltage. You can see this voltage. This is the gate voltage. This is current. Again, drain voltage, gate voltage, current, drain voltage. If you open it in the normal Windows, you transfer it into the normal Windows and open it. It will open like a CSV file, whatever I have shown you. Like this. It will have VGS at the rate VDS. For example, I have varied only 6 values of VDS. So it will show VGS at the rate VDS 0, whatever the current. Then VGS at the rate VDS 0.2. Next value of my VDS is 0.2. Then current. Then VGS at the rate VDS 0.4. Similarly, I will get the different CSV. Now using the Python code, I can simply convert it into form of LUT lookup table. That is read by the Verilog code. So this LUT table, now you can just wherever the Verilog code is there, you just paste that LUT there. So this code will automatically read. It is a simple Verilog code, Verilog A code, where IDS is simply it is reading this table. Simply it is reading this table. So what it will do, exactly what it will do, whenever you run the simulation, it will for example, if you have given the VDS value 0.8 and VGS value 0.6, so it will find out the value of VDS, VGS from the table, and with respect to that, it will find out the current. What is the current with respect, and it will give you the current value. So probably in the next class, I'll tell you how you can plot the inverter also. You can make the inverter also. That detail I'll give you in the next class. How to use it to make an inverter also. So for your assignments, I'll not give you to how to import it in the cadence. I will just simply give you to vary the different parameters. How to see the variation in the current with respect to doping concentration. How to see the variation with respect to temperature. Like that, I'll give you.
Sir, for assignment, what we need to do, I did not understand clearly.
So for assignment, what will be there? I'll just show you the question. For example, I'll give you one device, one DG MOS with certain combinations. The length should be the source length should be this, drain length should be this. You will be given some device. You have to make either you have to write the SCM for that, or you have to construct it in the SDE. And I'll give you certain parameters to vary. For example, I'll tell you to vary the doping concentration of drain. Just vary the 5 values of drain concentration and see the current. As I demonstrated you how you can vary the doping concentration. Similarly, I will tell you to vary the VDS voltage and see what is the effect in the current. Similarly, can give you three parameters. So I'll give you three parameters, and according to you, you have to plot the current.
Okay, sir. Okay.
You don't
Thank
have to go that much deep into how to use it in the cadence. That part, this is just for your future. If you want to work and if you want to see how you can import two tools, that is Centerus TCAD and Cadence. So that how you can use it, that's why I told you like that. And in the next class, probably I'll demonstrate you also by by importing it practically. I'll import it. I'll show you how. I'll show you that Python code also. If I'll have, I'll show you now also. And in the next class, I'll tell you that how you can use the Python code to convert it into a LUT, and that LUT you can import. Nowadays, the ML models, since the ML models are coming, and that Verilog can read the equation also. That weighted equation also Verilog can read. So you can use some ML model. That will also I'll demonstrate you in the next class how you can use that. So
okay, sir.
from today's lab, I'll just give you the whatever I have demonstrated you. That part will be there in the assignment.
Okay, sir.
Okay.
Actually, that process was little lengthy, so it was confused. Yeah.
No, that's why whatever the half lab will be there, na, that will be in the part of the assignment. The second part will not be there in the assignment. That is just for your demonstration. If you want to use it in the future, if you want some researchers, basically what they do, they make some device. They make some device, and what they do to benchmark it, whether your device is working right or not. There is whatever the changes you have made in the constructing that device. So for benchmarking it, they will import into the Cadence or ICC2. There is one tool of Synopsys also, ICC2, which is similar to Cadence. So they import that device into the Cadence or ICC2, and there they can compare the performance of their device with respect to normal GPDK 45 nanometers device. That's why I demonstrated that. But that will not be the part of your assignment.
Okay, sir. Okay. Thank you.
Okay. So that's from my side. In the next class, it will be 3D FinFETs plus I'll demonstrate you how to use Cadence.
Okay,
Sir,
sir.
I have one doubt. So
Yes.
when we were doing for three different temperatures, we saw it was failing. So how like I
That I'll
use
figure
the
out. That I'll
okay, sir.
figure
Okay,
out and I'll mention because I have to see what maybe I am doing some mistake with the temperature. I'll figure out and I'll show you, tell you that also in the next class.
okay, sir. Okay.
Okay.
So this assignment will be the deadline will be for how many? Like when will be the deadline?
Probably I'll post it tomorrow and it will be before 22nd. You have to just submit it.
Okay, sir. Okay, thank you.
Uh-huh.
So, sir, how many assignments we have to
Last
perform now?
assignment. This will be the last assignment.
Okay, okay.
And last, there will be one assignment which will be given by madam. That will be situated learning. That will be not will be related to the practical. It will be the theoretical assignment.
Okay.
That will be given by madam, Snehlata madam.
Okay, sir.
So
Okay.
this will be five marks, right?
This will be 5 marks. 7 plus 3, 10 plus 5, 15, and 5 marks will be situated. That is 20 plus 2 quizzes, 10. 30 marks EC1 component.
Okay, okay. Thank you.